Our world is more digitally connected than ever before, and emerging technologies promise to amplify this connection. Devices like smartphones, smartwatches, tablets, and laptops connect to Wi-Fi networks to provide instant access to information and entertainment, and that connection is made possible through signal processing. For Wi-Fi to work successfully, signal processing is used to overcome two main challenges: determining which devices can be active at all times, and decoding the information bits that are transmitted over the air. A household typically has only one form of internet connection, whether it be DSL, cable, or fiber optic, but has multiple devices talking to the same router. If you enjoy watching TV while also scrolling through your favorite apps on your smartphone, these devices must send signals to the same router to access information. To avoid the signals from colliding, Carrier Sensing Multiple Access, or CSMA, is used. CSMA forces every Wi-Fi device to be polite, meaning they observe the radio spectrum and sense whether a channel is available for it to use. When a Wi-Fi device occupies a channel, it specifies how long it needs the channel for, which allows other Wi-Fi devices to determine when the channel will be free. So, while someone might stream video on their laptop and use their smartphone at the same time, it's the unseen, rapid transfer of channel access in the airwaves that allows the use of both devices simultaneously and without interruption. But channel availability is only one step of successfully transmitting Wi-Fi signals. In an ideal situation, there is only one direct path between a device and the router, or direct line of sight. But signals can also be deflected off of the surrounding environments like walls, floors, and ceilings, creating multi-path channels. Each of these paths will have a slightly different delay, and the different delays in multiple paths cause signals to become entangled in the time domain. Signal processing engineers overcome this by using a technology called orthogonal frequency division multiplexing, or OFDM, that utilizes the concepts of time and frequency in signal processing. These frequencies are obtained by the fast Fourier transform, an algorithm that efficiently converts signals from the time domain to the frequency domain, and vice versa. Any signal can be represented by the sum of a very large number of sinusoidal waves having different frequencies. Think about the frequency domain as you would a piano. Each note represents a different frequency, but if you play a C note, the pitch you hear will always be a C note regardless of any reflection paths the sound takes. The fast Fourier transform enables OFDM to digitally decompose the multipath channel by dividing the bandwidth into small subbands, each carrying a different data stream. Because these subbands live in the frequency domain, the interference amongst the data streams is eliminated, thus avoiding the signal entangling problem in the time domain. As our world becomes even more digitally connected, future Wi-Fi devices will utilize multiple antennas and larger bandwidth. We need signal processing engineers to overcome new challenges that we have yet to face. Are you ready to solve them? Learn more through the Signal Processing for Communications and Networking Technical Committee of the IEEE Signal Processing Society.